Hello guys, welcome to Coder's Paradise. I am Anup Tiwari and in this video we are going to learn about the time complexity and space complexity. In this video you will learn about how to calculate the time complexity and the space complexity. Along with that we will also learn the importance of big O notation. So before we get started with calculating the time complexity and space complexity, let's just understand the importance of big O. So the big O notation means an upper bound to something. It means that we are bounding a certain value or providing an upper bound to something. For example, this is the upper bound. Okay, so now for example, let's suppose we have a equals to 5 and uh, we say that we let's suppose we don't know the value of a. We can also say that a is smaller than equal to 10. It means that a value can be anything. It can be 1, 2, 3, 4, 5. But we know that a cannot be greater than 10. It will be equal to 10 and smaller than that. So what we are doing is we are saying we are providing an upper limit to a, and hence we can say that a is bound to a particular value which it cannot be higher than. For a real world example, if I ask you what is your height, so in my mind I will be having an upper limit or an upper bound that your height cannot be more than 10 feet. Yeah, it is because I know if you can be taller, you can be 7 feet or can be 8 feet, but you cannot be more than 10 feet. we it is an upper bound to a particular height, height of a human being. So this is where the big notation comes. Whenever we are bounding some values to an upper bound, we used to donate is using big O. So what is the use of big O notation in our algorithmic world? So as we know that we have seen many examples where you have also seen that we say that the time complexity of an algorithm is big O of n. Someone said big O of n square. Someone says big O of root n. So it means that we are uh, kind of saying that uh, the total number of iterations that particular algorithm will perform is n. Says that total iterations algo will perform is n. Here n is the number of iterations. So number of iterations is a parameter using which we compare the two algorithms. If the number of iteration in an algorithm is less than the other, we say that algorithm X is better than algorithm Y because the number of iterations are less in algorithm X and number of iterations are higher in algorithm Y. Okay, so now let's just understand why we need to provide an upper bound to while comparing the two algorithms. So whenever we are trying to compare two algorithms, we always think about larger inputs, how our algorithm will perform for larger inputs. This is very important. We can understand this using a real world example. So let's suppose you are designing an streaming platform. Okay, you are designing an streaming platform. Okay, so this streaming platform is going to stream a cricket match. Okay, it will be streaming cricket match. So let's suppose while we are designing this platform, what you will be thinking in your mind? Are you thinking of a match? You will be thinking about how many users will be actively using my platform during a match, how many users will be viewing live on my platform. So to calculate the number of users, because your total all the algorithms, all the load, everything of your platform is dependent upon the number of users. So let's suppose then we have to keep factor of number of users. Now you need to design an algorithm inside this in this platform, which will handle, some kind of, you will do operations that will be very kind of a, the core of this platform. So now let's suppose you are, considering the number of users. So what you will, think, you will think about a match that is happening between Bangladesh and Ireland, where the number of users is kind of roughly say 100K. Okay, let's suppose 100K. Or you will be, kind of a thinking while designing the algorithm, so that what happened if there is a match between India and Pakistan, where the number of users is 1000K or 10,000K. So you will be always, thinking about the larger inputs, where the number of users or the number of, viewers are very large, and then you will be designing the algorithm. So that's why whenever we are trying to compare an algorithm or design an algorithm, we think in a manner that whenever the input size is larger, how our algorithm is going to perform. And that's why whenever we say that the time complexity of an algorithm is big of n or big of n square, we are putting an upper bound to that particular input, or we are saying that how our algorithm is going to perform for a larger input. Then we say that for a larger input of n, our algorithm will perform n iterations. N iterations or n square iterations, right? Now, as we have understand about this big O notation, let's just understand the factors that we need to, keep in mind while calculating the time complexity, or, while, finding the big O of n or big O of n square for a particular algorithm. So I will write it down. Steps to calculate the time complexity. Okay. So the step number one is find the total number of iterations. Second is remove the lower order terms. And third is remove the constant coefficient. Okay. So why we do this, I will just be explaining through an example. So let's take an example of the number of iterations of an algorithm. Let's suppose the total number of iterations of an algorithm is 20n square plus 30n plus 100. Okay. Let's suppose this is the total number of iterations or the total number of loops that is running in an algorithm. Now, the second step is to remove the lower order terms. So lower order terms are 30n and 100. So we'll remove them. Remove. This is our step 2. This is our step 1. We will remove. It will become 20n square. Okay. I will explain why we are going to remove and why we don't need it. But let's just find the time complexity of this algorithm. So now it comes to 20n square. Now the thing is remove the constant coefficient. So just remove this. So we will remove this. It is our step number 3. So we will get n square. So our time complexity will be big O of n square. Now, let's just understand why we remove this first lower order terms. So let's think in this manner. Is like, let's suppose for a larger, for not think about smaller inputs, but for a larger inputs, let's just compare. n square will be always greater than n or 30n. This is because for larger inputs, n square will be, growing at a much faster pace than 30n. For smaller inputs, might be, for an example, let's suppose I take a smaller input. We will take a smaller input 4. If we say n equals to 4, we can calculate here. So n square will be kind of 16, and which it will be smaller than 34s of 120. It is smaller. But let's now, but as we know, we don't compare algorithm based on, smaller inputs, but we think about the larger input. So if we are, changing it as a larger input for take it as 100. Okay, so it will be 100 square will be greater than 30 into 100. So it will be 100 will be always greater than 300. You can see. So for any of the larger values, the most dominating term will be the biggest, term in this equation. Because for the larger inputs, the highest order term will always be dominating in the equation. So that's why we need to negligate the smaller order terms, and we need to take care of, the highest order term. Now, moving to the step number 3. The step number 3 was this: remove the constant coefficient. So, do you think if I have written 10n square or 20n square or 30n square, will these constant terms be affecting this, the growth of this algorithm? For larger inputs, for anything, these n squares will be independent of these constant terms. Why? Because n squares decides the rate of growth. The rate of growth is dependent then upon n square and not on the constant value. That's why we need to remove the constant as well. And after removing, we found the most dominating term in the equation, which is the highest order term. And that's why we select this as our, the main thing for our algorithm, deciding the time complexity of the algorithm. And we can say that the time complexity of this algorithm is P of n square. So hope this thing is clear to you. And we will be discussing more examples, more problems later on. As we start solving other problems, we will be calculating the time complexity and understanding how we are going to calculate a time complexity. In next video, I will be explaining a bunch of examples with the code, and we will try to calculate the time complexity and the space complexity of that. Before that, let's just talk something about space complexity as well. So space complexity. Okay. So space complexity is defined as the extra space, the space taken by the algorithm. Okay, it is a space taken by the algorithm. So, for example, let's suppose I have an algorithm. Let's make a function which is taking an integer array input a of size n. Okay, just just hold on. Okay, mhm, of size n. Okay, we are having a function here, and we are saying that there is an integer x, there is an what is happening to my pencil? Yeah, I have a float y. Okay, now let's just take some other examples as double d. Okay, and we have double D, and we have Boolean E. Okay. So the size of an integer is 4 bytes. It's depend upon the programming language, but mostly we consider it as 4 bytes. For the float, it will be again 4 bytes. For double, it will be 8 bytes. And for Boolean, it will be 1 byte. Okay. Now, if we are using any of these variables, okay, we are using a fixed kind of size. So always considering a variable, we are going to say that the space complexity will be big of 1. We are not using any extra space that is dependent upon the input we are taking on. Okay, it is a constant thing. So or the time complexity will, we know that in space complexity we have understand that while calculating the space complexity we need to remove the constant fields. So here as well we don't consider these values as extra space in our program, so we remove this. Now where we need to consider the space, so let's suppose taking the previous example only, we have a function where I have written integer array A with size n. Okay. Now, if we are inside this, we are going to, create another integer array ARR with size of n. Okay. And we are going to do some operation. Then here we can say that we are going to create an integer array ARR with size n. So now this size n is dependent upon the input size provided here. Okay. So it is dependent upon the whatever the input we are providing. So it will be growing, the size will grow as the input grows. So that's why here we can see that the space complexity that we are using is big of n. Okay, because this n, the size of the internal ARR array is dependent upon the input size where we are providing. That's why we need to consider this as an extra space, and we can say that the space complexity of an algorithm is big of n. Now we will take a very good short example to conclude on this, and then in the next video I will explain you a bunch of examples where we will totally understand different algorithms with different time complexity, and we try to analyze different examples to find the time complexity. Before that, let's I will provide you one thing where you can know which time complexity is better than which. So here we can start with that. So we can say that the best time complexity is big of 1. Okay, where there is no loop, nothing, it just in one shot it is big of 1, which is constant space, we can constant time, we can say that it is running in constant time, which is again big of log base to n, is faster, is kind of a slower than big of 1. Then comes in big of root n. Then comes in, just a minute, big of n, sorry, my bad, big of n. And then we have our big of n log n. Then we have big of n root n. Then we have big of n square. Then we have big of n cube. And then we have big of 2 to the power n. So this why I'm providing you this, like whenever we are going to calculate in the next video we are going to find different algorithm, then we will use this data to find which algorithm is better. So with all those things, in the next video, we will discuss, a bunch of examples, more than 20 examples we will discuss, or 15 to 20 examples we will discuss, where we will, learn how to find the algorithm. We will, go to different situations and all. So so this is all for this video, and hope you will like this video. Make sure you like the video, subscribe my channel, and please turn on the notification so that whenever I'm going to upload my video, you will get notified. And Happy learning. We'll see you again in the next video. For now, have a good day. Bye bye.